In this video, we'll be learning about center of mass and the conditions for equilibrium. The center of mass of an object is the point on an object where a single force will not produce a torque. That's when only one force is acting on the object. In other words, if we were to take the object out into space where there is no force of gravity and exert one force on the center of mass of the object would not rotate. It would simply move in the direction of the force applied. I have a video that talks about the center of mass trajectory. This is a video from the MIT Department of Physics where two people will be throwing objects. They will first throw the object in the light, so you can actually see the object moving in a parabola, and then they will throw the object in the dark. When they throw the object in the dark, they will first spray paint the center of mass, and you'll watch the trajectory of the center of mass. After that, they will spray paint the center of the object, showing that the center of mass is not necessarily always in the exact center of the object. Let's watch and see. Hopefully you were able to notice that the center of mass follows the traditional parabola path that we learned about when an object is in projectile motion, and the center of the object does not necessarily follow that path. Specifically, when an object is thrown in the air, all points on that object will rotate about the center of mass. Well, how does this deal with the problems we've been working on, these net torque problems? This relates to these net torque problems because the force of gravity on an object is exerted at the center of mass. That means when we're looking at a net torque problem from here on out, we're looking at all the forces acting on it, we will include the force of gravity, and the force of gravity will be located at the center of mass of the object. For a uniform object, an object where its mass is evenly distributed throughout, and it has a regular shape, the center of mass is at the center of the object. What does it mean if an object is in equilibrium? Hopefully you answered that it means that the acceleration of the object is equal to 0, and therefore the net force on the object is equal to 0. We learned this back in chapter 4, in the chapter all about forces. So I have here an object that is acted on by only two forces. We're ignoring the force of gravity again. Each force has a magnitude of 10 newtons. Is the object in equilibrium? Why or why not? If you have something nearby that you can try this out, go ahead and do it. You won't be able to ignore the force of gravity here on Earth, but you can still get a picture for what's going to happen. Maybe you tried it, or maybe you can just figure out that this object's going to rotate. And if something's rotating, it is not stationary, or it definitely has an acceleration. It is accelerating because it's moving in a circle. Therefore, it can't be in equilibrium. Something that is speeding up or slowing down is not in equilibrium. That counts for rotation as well. Now we have two conditions for something to be in equilibrium. The two conditions are that the net force must be 0 and the net torque must be 0. This is what it truly means to be in equilibrium, when both of these two things are equal to 0. We'll use these conditions in the next few problems, starting with example number 6. In this example, we have a meter stick that is supported on the left by a fulcrum, and this fulcrum exerts a 10 Newton upward force on the meter stick. A fulcrum is simply something that you put underneath an object to keep that point of the object stationary. There's an additional 40 Newton force that's applied at the 80 centimeter mark. We want to know what other forces required to keep this meter stick in equilibrium, and where must this force be located. We'll start off looking at a net force equation. We know that the net force acting on our object must be equal to 0, and in this case we have three forces acting. We have the force of gravity, the force from the fulcrum, and this applied force. But it tells us that there's some other mystery force that is being applied to this object, to this meter stick, to keep it stationary. So really we have four forces. Those four forces again are force of gravity, applied force, force from the fulcrum, and our mystery force. Just as we did back in the force chapter, we'll look at a net force in the x and net force in the y direction equation. In the x direction, we have the x component of this applied force, and we must have an x component to our mystery force. I'm going to call that F unknown and use U for unknown. Those two added together must equal 0. In the y direction, we have the force of gravity, the force from the fulcrum, the y component of our applied force, and possibly a y component to our unknown force. All those added together equal 0 as well. Okay, so let's start off and figure out what we already know. The applied force in the x direction is equal to the negative unknown force in the x direction. I know that the applied force in the x direction, or the applied force, has a magnitude of 40 newtons at an angle of 35 degrees. So I can find that x component. That'll help me find the x component of the unknown force. To find that component, I'll take the magnitude 40, multiply it by the cosine of 35 degrees, and that gives me 32.766 newtons. Looking at my diagram up here, I notice that that x component would be negative, and so the two negatives cancel each other out. So the x component of my unknown force is simply 32.766 newtons. Let's now look at the y components. The unknown force in the y direction is equal to negative Fg minus force of the fulcrum minus Fay. We are told that this is a 2.5 kilogram meter stick, and a 2.5 kilogram meter stick has a force of gravity of 24.5 newtons. We know that force of gravity is always pointed downward, so I would plug in negative for force of gravity, which cancels out the negative sign in front of the Fg. The problem tells us that the fulcrum exerts a 10 Newton upward force on the meter stick. So I plug in positive 10 newtons. And then I have to calculate the y component of this applied force. I do that by 40 newtons times the sine of 35 degrees. And I notice that it is up, and thus it is a positive component. So the component that I get is 22.94 newtons. When I add all of this together appropriately, I end up getting negative 8.44 newtons as the y component here. So I have an x and y component of my unknown force, which means I can calculate the unknown force itself. Go ahead and pause the video and do that for yourself right now. You should have found that the unknown force is 33.84 newtons, and the angle you should get is 14.45 degrees. Because I have a negative y component and a positive x component, that means that this angle is south of east. We have now accomplished half of what this problem asked us to do. We found what the additional force was, but we don't know where this force must be located. To determine that, we need to use net torque equations. Again, for this object to be in equilibrium, net torque must be equal to 0. Well, we have four forces possibly causing a torque here. We have the torque from the force of gravity, the torque from the force of friction, the torque from the applied force, and the torque from our unknown force. Those all added together have to be equal to 0. Well, looking at the problem, a logical place to put the fulcrum, or to put the axis of rotation, is at the fulcrum. That's a point on the meter stick that cannot rotate. So, the force from the fulcrum is not going to apply any torque, because the distance, the r value, is 0. So I can cross out that torque. The remainder of these forces do apply a torque. So I have the force of gravity times the radius for the gravitational force times sine theta. That's the torque from gravity. I have the torque from the applied force. That's equal to the applied force times the radius for the applied force times sine theta. And the torque from the unknown force, which I can't calculate yet because I don't have a radius. Let's calculate these two first. We already found that the force of gravity is 24.5. The radius is the distance from the axis of rotation, or this left end, to where the force of gravity acts. This is a meter stick, which means it's a uniform object. So the force of gravity acts at the center. Therefore, the radius is 0.5. So 24.5 newtons times 0.5 meters times the sine of the angle between the radius and force vectors. Well, in this case, the radius vector points to the right, and the force vector points directly down. So my angle is 90 degrees. Therefore, the torque caused by the force of gravity is equal to 12.25 Newton meters. Looking at my diagram up here, the force of gravity would be straight down, and it would cause a clockwise rotation. Next, I have the torque from the applied force. The applied force we know has a magnitude of 40 newtons, and the problem tells us is applied at 80 centimeters. So 40 newtons times 0.8 centimeters, times 0.8 meters, times the sine of the angle between the two. Looking at this here, we see that we're given an angle of 35 degrees. But is that the angle between the r and the force vector? Let's take a look. There's my r vector. Now that I've drawn it, I will place it tail to tail with my force vector. And you see that 35 degrees is not the correct angle. That's the angle that we want. Well, how do we find that angle? We'll have to use a little bit of math to find that angle. If I continue this horizontal line to the left, I see that this small angle right here is an alternate interior angle to that 35 degrees. So it is also 35 degrees. That means that my large angle, the one that's outlined in blue there, is 180 minus 35 degrees, or 145 degrees. So that's the angle that I plug in there. And I find that I get a torque that is equal to 18.35 Newton meters. Looking at the direction of that torque, this is pushing up on the rod. The rod cannot move on the left end, so this right end would move upward, causing a counterclockwise torque. Back up to my net torque equation, I see that these two torques added together must equal the unknown torque. Or another way of saying is that the unknown torque has to be negative torque of gravity minus the applied torque. Well, plugging in numbers that we already know, we have that the torque of gravity is 12.25 Newton meters, and it's clockwise. That makes it negative. So a negative times a negative gives me a positive 12.25 Newton meters. Then I have the applied torque, which is the torque from the applied force. That's counterclockwise, so it's positive. (12.25 Newton meters minus 18.35 Newton meters gives me negative 6.10 Newton meters. Or 6.10 Newton meters clockwise. What I'm looking for is the radius. I know the magnitude of this unknown torque is equal to the radius times the unknown force times sine of theta, which means the radius is equal to the unknown torque divided by the force times sine theta. Again, magnitudes only get plugged into this equation. So I have 6.10 Newton meters. And my force was 33.84 newtons. And the angle that we gave for that unknown force was 14.45 degrees. As long as that angle is measured with respect to the horizontal, that's the angle you can plug in here, because my radius vector is horizontal. So I plug this all in, and I find that this unknown force is located at 0.723 meters, or the 72.3 centimeter mark. I know that this answer is logical because it is located somewhere on the meter stick. If you had gotten a number that was larger than 1, you would know that you did something wrong. So you'll notice to find all of this information, we had to use both net force and net torque equations. It took some work. These problems are not quick, easy problems. But let's try one more. This one talks about a window washer standing on a scaffold that is supported by 2 vertical ropes. The problem wants us to find the tension in each rope. Let's start by drawing a picture. There's my scaffold. It tells me the worker standing 1 meter from the left end. Looking at the forces on this scaffold, I have 2 tensions. I'll call this left one TL and this right one TR. I know that the scaffold has a weight of 200 newtons, and that is immediately at its center. And the man also exerts a force of 700 newtons on this scaffold. So we have 4 forces acting on here, and they're all in the vertical direction, which is wonderful because it means we only need one net force equation. For this net force equation, I have the 2 tensions plus the force of gravity plus the force from the man, and that all added together must equal 0. I don't know anything about the 2 tensions, TL and TR, but I am given numbers for the force of gravity and the force of the man. Both of these are in the negative direction because they're pointed down, so when I plug in the numbers, I'll plug in a negative. Negative 200 newtons, and there's a negative in front of Fg, so that cancels to be positive, minus a negative 700 newtons. That tells me that the left tension plus the right tension must be equal to 900 newtons. Just based on this information, I don't have enough to be able to solve for each of these tensions separately. So I must use a net torque equation as well. On a problem like this, where it is not immediately certain where the axis of rotation is located, you may choose an axis of rotation. You want to choose an axis of rotation that is logical, which means in this case, you want to choose an axis of rotation where one of your unknown forces is located. I'm going to choose the left end to be my axis of rotation. I like to make a note to myself so that I remember as I'm making this net torque equation. Because the axis of rotation is at the left end, that left tension will not have a torque. Its torque will be 0. So I have 3 other torques. The torque from the right tension, plus the torque from gravity, plus the torque from the man. Those all added together must be 0. Okay. So the torque from the right tension is that right tension times the radius for the right tension times the sine theta. This time, instead of calculating it separately, I'm just going to plug it into this above equation. Looking at that right tension, it pulls up, and with my axis of rotation at this left end here, it would cause a counterclockwise or positive torque. Next, I have the force of gravity. Looking at the picture, the force of gravity pulls down. It would cause the right end of the scaffold to move downward, which would be in the clockwise direction. So I will subtract from this first expression the force of gravity times its radius, I'll call that Rg, times the sine of theta. Similarly, for the force from the man, it's pointed downward, and it will also cause a clockwise torque. So I subtract that as well. All these things added and subtracted equals 0. Looking at my picture, my radius is always going to be horizontal. My forces are all vertical. That means my thetas are all 90 degrees. And the sine of 90 is 1. So I'm going to cross those out so I have less to deal with. The right tension is my unknown here. So I will eventually solve for that after simplifying my equation. To solve for this tension, I will add these two terms to the other side, and then I'll divide both sides by this radius. So that this force of tension is equal to Fg Rg plus Fm Rm divided by the radius for that right tension. Fg is 200 newtons. The radius for the force of gravity is halfway through the scaffold. The scaffold is 3 meters long, therefore the radius is 1.5 meters. We know the force of the man is 700 newtons, and it tells me that he is standing 1 meter from the left end. Finally, the radius for the right string is 3 meters, the length of the entire thing. Plug that all into my calculator, and I find that the rightmost tension, TR, is 333.33 newtons. That's one of the two values I'm looking for. Now, I can go back to this equation here, which tells me that the two tensions added together equal 900 newtons. So 900 minus 333.33 is equal to 566.67 newtons. And that's the tension in my left string. Hopefully this one made sense to you and you're ready to try one on your own. And that's this last problem. This is similar to the previous one, except for this time we have 3 strings, 3 ropes that are exerting a force, a man standing on this plank. It is a uniform plank. That means the force of gravity acts at the center of mass, which is at the center, and we're looking to find the tension on each rope. I want you to try this one on your own and bring it to class with you the next time we meet.